Okay, hi Year 12, it's Mrs. Horton here. I'm going to do a video today on how to construct a Born-Haber cycle for aluminium oxide, formula Al2O3. This is the question, it's question 1 on worksheet 2 of Unit 9. I've done a previous video when I could still get into school on how to do a Born-Haber cycle for question 3, which is potassium chloride, which actually is more straightforward than doing it for aluminium oxide because you've got the ratios are in a 1-to-1. So what we're going to look at here is how to use these values to construct a cycle when you have multiple charges on your ions. Please bear with me. These videos are out of my comfort zone. I absolutely detest myself on camera. And I'm working in my daughter's bedroom so that the kids have got downstairs, which is why there is pen all over this pretty ropey desk. So if you have this worksheet open with you, then you will be able to follow along with the values as I plug them in so that you can see what we're doing. So first things first, we need to draw the bottom line of our cycle, and on there we're going to put our ionic compound, which actually has got quite a high degree of covalent nature, and that's something that you need to get a thinner pen that you need to be able to explain. So where the where the experimental values differ from the theoretical values for these Born-Haber cycles, for these enthalpy changes, you need to be able to explain where you would have the greater difference in those values, and that comes down to what degree of covalent bonding exists in that ionic compound, and that's to do with the size of the cation, the size of the anion, and the charge on those cations and anions, but that's in a further lesson. So first of all then, we've got our ionic compound, which is a solid, and then we're going to come up from there, and on this line we're going to have our elements in their standard states, which for aluminium is a solid, it's a metal, and for oxygen is a gaseous molecule, O2. Now currently they are not balanced because in our ionic compound we have aluminium oxide, Al2O3. We obviously cannot just pop a 2 there because that would imply that aluminium is diatomic, which it is not. It is a metal, so we need to say 2Al. Next, we've got 3 oxygens down here. We can't just change that to a 3, obviously that doesn't work. We can't just put a 3 in front, that would give us 6 oxygen atoms. So we're going to say 3 over 2. And that gives us our balanced atoms in their standard states. Now, the enthalpy of formation from our elements in their standard states to the ionic compound is an exothermic process. Energy is given out during that process. We're bond making. So the arrow is going to point downwards for that. Okay, so next thing then, we're going to atomise our aluminium. Remember, we atomise, then we ionise, and then finally we combine in the lattice enthalpy. So we're going to go from 2 aluminium atoms in their standard state to 2 gaseous aluminium atoms, and currently we've done nothing to the oxygen, so that stays like that. That is an endothermic process, the arrow's going upwards. Okay, so we've atomised our aluminium. Next up we're going to atomise our oxygen. Oxygen already exists as a gas, but it exists as a gaseous molecule, and we want gaseous atoms. So we've got 3 over 2 times 2, so we have got 3 gaseous oxygen atoms. So now we have got our gaseous atoms, they're balanced, we're ready to start ionising, and I'm going to run out of space here because aluminium exists as a 3+ ion, which means we're going to do the first ionisation energy, we're going to do the second ionisation energy, and then finally the third ionisation energy. So I'm going to try and make my gaps kind of small, but remember these gaps, actually the size of them does reflect the magnitude of the enthalpy change. Mine do not. because I'm just trying to fit it on the board. So first of all then, we go up. Remember, ionisation energy to remove 1 mole of electrons from 1 mole of gaseous atoms requires an input of energy. And when you look at Unit 8 in conjunction with Unit 9, you'll look at the trends down groups, specifically Group 2, as to the magnitude of those values, why it's bigger or smaller. So we go from 2 moles of aluminium atoms to 2 moles of aluminium 1 plus ions. We've done nothing yet to oxygen, but we must remember that we have removed electrons, and so those now need to feature in our equation. We've got 2 aluminium atoms, so actually what we've got here is 2 electrons. I'm just going to rub out this because otherwise I'm going to run out of space. So I'm going to come up again to form my aluminium 2 plus ions. Again, oxygen, nothing's happened yet. And so now I'm going to have 4 electrons. Finally, just come up here. My third ionisation energy gives me 2 aluminium 3 plus ions, always putting in our state symbols, really important. And that's going to give me 6 electrons. And those 6 electrons are then going to combine with the 3 oxygen atoms, and that's going to give us 3 oxygen 2 minus ions. So oxygen, as we just said, forms a 2 minus ion by way of a 1 minus ion. So you will recall that the first ionisation energy, the first electron affinity is an endothermic process. Okay, energy is given out because essentially it's kind of bond making. So we're going to have an arrow coming down, and we're going to combine 3 of the 6 electrons here to form 3 oxygen 1 minus ions. So we're going to have 2 Al3 plus 3 O minus, still gas, plus 3 electrons. We've used 3, we've got 3 left. However, the second electron affinity of oxygen, I'm going to come up here, but these spacings are not the best. The second electron affinity, I'm just going to put there first EA, second EA, is an endothermic process. It requires energy to combine a second or a third, indeed, electron, because you are trying to add something negative to something negative, and to do that you need to put some energy in. So we're going to come back up, and we're then going to have 2 aluminium 3 plus 3 O2 minus. There's no electrons in that equation anymore because we've used them all. Okay. Right, so I'm then going to draw an arrow all the way down to here, and that is our lattice enthalpy, and I believe that that's what the question asks us. Yes, that's what the question asks us to calculate. So, exactly the same as before, we need to calculate the enthalpy change on this side, and that's going to equal the enthalpy change on this side. Now you can see, remember, lattice enthalpy is always an exothermic process. This is a highly exothermic process, lots of energy released. So coming up here, first thing we need to do is identify obviously which process matches which value. You need to remember for this one that you have got multiple atoms. You've got 2 aluminium atoms and you have got 3 oxygen atoms, and you need to account for that in your calculation. And in actual fact, what I'd like you to do when you are answering these questions, if you get one in the exam, and I'm running out of space on my board, so I'm just going to write it on here, I'd like you to annotate the answer with 3 things. 1, multiples, 2, electrons, and 3, sign. And then I want you to consider those things as you answer the question. Are there any multiple atoms, and have you accounted for that in your calculations? Have you got electrons in your equations, because they're really easily missed? If I asked you to write the ionisation energy equation for something, you definitely include electrons, but for some reason when doing these ones, they tend to get left out. And then finally, sign. So if what you're calculating is exothermic, have you got a negative sign in front of it? Because if not, you're not going to get the mark. So let's just, is that back in shot? Goodness only knows. Right, there we are. So looking at the values we've got here, enthalpy formation. So this is minus, oh, blooming heck. Sorry. Should check these pens right. Right, minus 1675.7. Okay, and again, if you follow along on your sheet, you'll be able to see these values. So then we've got the heat of atomization, or enthalpy of atomization, to go from one aluminium atom as a solid to one aluminium atom as a gas, but we've got two of those, so we're going to need to say 2 times 324.3, and the same goes up here. So we have got 3 oxygen atoms. Okay, so we're going to say 249.2 times 3. Okay, then we're getting into our ionisation energy, and we're going to need to multiply all of those, the first, the second, the third, by 2. And I think actually, if you just bear with me 1 second, I have got some pre-calculated values somewhere. So we've got, so these are the calculated values, the 2 times, so that's going to be 1156, second is 3634, and the third is 5490. As I say, that I have already multiplied those values by 2. That is the final answer. Okay. Right, we've then got our first electron affinity. Again, remember that we have got 3 oxygen atoms, so we're going to say 3 times the value on the sheet, and that gives you a total value of minus 424.4. And for the second electron affinity, again, we've got 3 atoms, so we're going to say 3 times the second electron affinity, and that gives you a value of plus 2372.4. So what we then need to do is to work out the difference between here and here. Okay, so we're going to say 2372.4 minus 424.4, and that gives you 1948.2. That value is then going to get added to there, because we have gone up, if you like, by that amount. Okay, so that is going to get added to all of those. All right, once you do that, that should give you a value of that, and that, because that side is equal to that side, is going to be your lattice enthalpy. But remember to check the sign. That is an exothermic process, and so we're going to put a minus there, and the unit is kilojoules per mole. Okay, so that's constructing a Born-Haber cycle for an ionic compound where you have multiple ions with multiple charges, for example, aluminium oxide.